BC Calculus, Lesson 5.5, Linearization and Differentials. So, try and exercise. I'm not actually going to do this, but it's great exercise to try. If you follow this graph, you'll see that you get a graph that looks a lot like a cusp, to which we've all been taught, oh, we can't differentiate that. But then you look at this and you say, yeah, I can differentiate that. You do all your math and you find out the slope is at 0 is 0, and this has a horizontal tangent of y equals 1. So you say that's not possible. So you keep zooming in, and if you've zoomed in enough, you will see that, and I mean a lot, sure enough, right there, zoomed in, the function looks like a line. So it's a little pump fake. It's a good example of, be careful making assumptions, but it also shows you that if you can take a derivative, then there will be a tangent line there, no matter how much it looks. We're a little over-reliant on our calculators, which I don't have a big problem with, but we need to be aware of these things at all times. So when you get in there, it looks like they match up. A bizarre zoom in would be something like this. It actually looks almost like a parabola when you zoom in at a certain time. And again, so it has a tangent line at the point 0, 1. The slope equals 0. Therefore, the equation is y equals 1. So, this gets us to the concept of linearization. Understand, linearization has to be taken at a point, or very close to a point, I should say. And that point is called the center. And you need to be always aware of that. It's very, very important that you say, okay, here's the center. So, here's the linearization, and it looks a lot like a derivative definition. And it is, it's similar. We're using a derivative to approximate what the equation of a line is for a really short time around some center point. So it's, it's actually the same, just nearby. And several people have pointed out to me, well, how near do we have to be? And I say, I don't know, but that's a good question. So let's just try one and see how it goes here. First thing we do is we plug 0 in. We get out 1, and I'm going very quickly. So if you need to pause this, go ahead. Then we take the derivative, and we get 1 over 2 root 1 plus x. We plug in the point we care about, 0. We find out we're looking at 1 over 2 for a slope. And then we say the linearization is 1/2 x minus 0 plus 1, also known as 1/2 x plus 1. So let's approximate it. Big debate about this. What do we plug in? Well, it's got to be close to the center of 0. So it's got to be near there. That's the number we plugged in. We didn't plug in 1.02. We plugged in 0. So we're going to plug in 0.02. And we go 1/2 of 0.02 plus 1 equals 1.01. On a calculator, we plug in square root of 1.02 and we find it is 1.00995. We subtract these two and we say the error is 4.05 times 10 to the negative fourth. And we say that is less than 1 times 10 to the negative third. Times 10 to the negative fifth if we put it in the calculator and subtract it. And then gives me 1 times 10 to the negative fourth. The error is less than. So you'll see that in my answer key. So let's try it again. Plug in pi over 2. Get out pi over 2 comma 0. Take the derivative. In the interest of time, I'll keep it very, very quick. Negative sine of x. Put in pi over 2. Of course, it equals negative 1. I feel like that's wrong. No, that's right. And then we linearize it. Negative 1, x minus pi over 2 plus 0 equals negative x plus pi over 2. Check it for 1.75. Whoa, wasn't it 1.75 minus pi over 2? No, this was our center. Now we're looking at spots next, left and right of it. Oh, by the way, pi over 2 is like 1.57, approximately. So we're actually pretty far away. We're 0.18 away. That's a lot. But if we plug that in, we will find we get negative 0.178. And if we just did cosine of pi over 2, pardon me, of 1.75, we would get, my mistake. This is negative 1.75 plus 1.57 is negative 0.18-ish. And in the calculator, negative 0.178. So it's close. It's really not that far off, which is surprising. So again, the error is less than 1 times, in this case, 10 to the negative third. You can play with that and see where it takes you. Now, in a previous example, we found that we could approximate 1 plus x to the 1/2 for numbers that are small, close to the center, at approximately, well, if we center it at 0, close to 0, approximately 1 plus 1/2 x. And that seems totally insane. Here it is. So I say, no, let's check this out. And we distribute out 1 plus x to the third. I've already done the second part. We get 1 plus 2x plus x squared over x plus 2x squared plus x to the third. We get 1 plus 3x plus 3x squared plus x to the third. You say, see, it doesn't work. Well, if x is really, really small, these are going to basically vanish. This is actually not a bad approximation. And by the way, if you're lost on what's going on here, don't feel bad. It's pretty common. So, how would we use that to do these problems? Well, we rewrite them. So we've got this one we rewrite as 1 plus negative x to the 1/3, which is 1 plus negative 1/3 x. This one is the same as 1 minus x to the negative first. Always want to write it as plus. 1 plus negative x to the negative first. So this is the same as 1 plus x. This is the same as 1 plus negative x squared to the 1/2. So once we blast it out, 1 minus 1/2. That would be more accurate, because the negative does not get squared. 1 minus, it does it. Oh, it does it to the negative 1/2. 1 plus 1/2 x squared. And here, 1 plus 5x to the fourth to the 1/2, we get 1 plus 5 over 2 x to the fourth. So, got some interesting applications of this concept. We can use it to approximate things. We say f of x equals square root of x. We say, what number do we want to use that's pretty close? We'll say, let's use 121. When we take square root, we get 11. So find the derivative. 1 over 2 root x. Find the derivative of at 121. Get 1 over 2 times 11 is 1 over 22. And our linearization is 1 over 22, x minus 121 plus 11. Plug in 123. And we're using this to approximate because we're pretty close. We would get 2 over 22 plus 11, which in this case is 11.09. Technically 09 repeating, but I'm not going to get into that. If we take a calculator and we say, what's the square root of 123, we will find that we get 11.09. So they're actually a pretty good approximation. It's kind of cool. This one we will say f of x equals the third root, and we'll use 125. Third root of 125 is 5. F prime of x equals 1 over 3x to the 2/3. F prime of 125 equals, third root is 5 squared is 25, 1 over 75. Linearization is 1 over 75, x minus 125 plus 5. Interesting. Put 123 in, and we get out 4.973. Take the third root of 123, and we get 4.973. Kind of neat. So this gets us into the concept of differentials, these small changes. And Leibniz, the German founder of calculus, as opposed to Newton, the English founder of calculus, used dy dx to represent the derivative of y. Everybody looks at that and says, oh, it's two things being divided. It's actually a limit of two things being divided, but we're not getting into that. We can just look at them as things. dy is on its own and dx is on its own. So we can rewrite it, instead of dy dx, we kind of throw the dx up here. And this takes some getting used to, kind of like implicit differentiation, but it's really not that hard. You just leave the dy off and throw it in over here. And then we can calculate things. dy equals 5 times 1 to the 4th times 0.01 plus 37 times 0.01. And we will get 0.42. So it is chain rule-ish. You're always going to take the derivative of the inside, regardless, even if it's vanished, like in this case. Derivative of 37x is 37, still dx is thrown in there. And if you want, you can just look at this as dy dx to your derivative and throw the dx up at the end. And a lot of people actually do it that way. dy equals cosine of 3x times 3 times dx. dy when x is pi and differential is negative 0.02 equals 0.06. You can also do it implicitly. dx plus dy equals, leave it, dy plus dx, leave it. Problem, I don't know what y is. Gotta go back here, plug it in. 2 plus y equals 2y. And 2 equals y. Good. So now we come back and start plugging things in. And we could solve this for dy, but there's really no point. I mean, might as well just blast it out. dx is 0.05 plus dy equals 2 dy plus 0.05 times 2. dy equals 0.05 minus 2 times 0.05, negative 0.05. Making sure I did my work right. Yeah, look at that. I did it right for a change. Scary. Note, sometimes you'll see df instead of dy. It's like, oh, we have a function and we want to take the derivative. We'll just call it df instead of f prime because we're leaving dx's all over the place too. Not a big deal. So more practice. There's no y. Just take the derivative with respect to whatever variable is there. Can't do this implicitly. We have to have a single variable. So derivative of tangent of 2x is secant squared 2x times 2 times dx. Always like to leave that dx at the end. Kind of looks aesthetically pleasing. And this one is x plus 1 dx plus x dx equals 2x plus 1 dx. That's wrong because I forgot the entire bottom. X plus 1 squared equals, and this is an interesting way to write it, and that's a minus, x dx plus cancels 1 over x plus 1 squared dx. That's typically how it's done. You could also put the dx there on top. Interesting stuff. So let's put it together, linearization and differentials. We're moving a small amount of this dx. We can use the linearization to find out how much the function changes. And this is the differential estimate of change. Here's the definition here. All right. If it's differentiable, the approximate change from a to a plus dx is df equals f prime of a. Notice just a, not a plus dx, times dx. So a little bit of memorization there because that's it. I mean, area of a circle is pi r squared. Want to know what dA is? When we increase the circle's area from 10 to 10.1. So dA, the change in area, equals 2 times pi times 10, which upsets people a little bit, times 0.1, the change. So that is sorry, a little trouble with the calculator. 2 pi meters squared. Notice we started this lesson with linearization, which is an approximation. So we're still approximating because the actual change, the delta A, this is the actual change, would be pi times 10.1 squared minus pi times 10 squared, which is about 0.01 pi. Pardon me. I have to put this in and blast it out. 2.01 pi meters squared. Estimate about 2 pi. Actual about 2.01 pi. The difference, what we call the error, and again we were just approximating, 0.01 pi meters squared. So here's the definition, because we just kind of slapped something up there. The actual change, delta F, the estimated change, dF. The relative change, delta F, over what we got for F. The percentage change, delta F, over what we got for F of A, times 100. And estimated is just when we put the dF in instead. So, do it all. Inflating a bicycle tire changes the radius. Use differentials to estimate the change in perimeter. So perimeter is circumference. It's 2 pi r. dc equals 2 pi. Notice there's no r in that. A little freaky. So, where do we go from here? Disappointed. dr. So, dc equals 2 times pi times 1. That's the approximate change. The actual change is 2 pi times 13 minus 2 pi times 12, which is 2 pi. So they're actually the same. Nothing has changed. The absolute change is the same as the approximate change. So there it is. Let's make sure we got them all. Absolute change is 2 pi. The relative change is 2 pi over the original, 24 pi, about 0.08. And then the percentage change is just going to be that times 100, 8%. So here we go again. Assume that the Earth is a perfect sphere. With the radius of this, what effect would the tolerance have on our estimate of Earth's surface area? Surface equals 4 pi r squared. ds equals 8 pi r dr. R equals 3959. dr, this bothers people, equals 0.1. Do not have to count for the plus minus. So we estimate things. We'll say, hey, let's run with this. 8 times pi times 3959 times 0.1. So our estimate could be off by as much as 9,950 miles squared. So what's the point? The point is that, hey, we're just going 0.1. Well, it turns out that makes a pretty big difference. You got to be really, really careful. Another problem, how accurately should we measure the radius of a sphere to calculate the surface area within 1% of its true value? So we want our inaccuracy to be small enough to make the corresponding increment in the surface area satisfy this inequality. The absolute value of change of S is less than or equal to 1 over 100, that's the 1%, S. And S, of course, is 4 pi r squared over 100. So you know we're going to have to take this ds somewhere. We're going to approximate this with ds equals 8 pi r dr. And the question we're asking is, how accurately should we measure the radius? So that's going to be our dr. So we plug it in, 8 pi r dr less than or equal to 4 pi r squared over 100. Divide by 8 pi r. We get dr less than or equal to pi by 2 times by r over 200, which is approximately 0.005 r. So we should measure r no more than 0.5% in our error. A lot going on there. So we're actually going to call it there, and we'll leave this as part 1 of linearization and differentials. There's a fantastic amount of material there, so happy mathing.